So today I'm going to talk about laser plasma X-ray sources. It's a bit more pedagogical. Camilo asked me, especially for the master students, to talk a bit about that. And then in a second part of the talk, I will talk a bit more about machine learning techniques. Two small disclaimers already. Nowadays, everything is basically machine learning. It's also things that we've been using for decades. And in particular, there's, for instance, a problem of optimization, which some consider to be now part of machine learning, some don't. To keep this more introductory, I mostly talk about optimization problems in a more general way and give a few examples how you can tackle them. I'm recording this talk and will share it afterwards with you because basically this could be many lectures, and in some parts I will have to go a bit quicker than people might want who haven't seen these things before. So I give some indications on the slides, like how you can follow it, and so you can look at it later again. So first part, I will talk about the X-ray sources. And well, as a general idea, we have our electromagnetic spectrum, and when we talk about X-ray, or I talk about X-ray, usually means something which is in this range of a kilo-electron volt to well, many hundreds of kilo-electron volts. Some people consider that gamma ray, but for the sake of what we're talking about, it's basically the same. We use the same mechanisms to generate them. But I'm not going to talk about something like extreme ultraviolet, where there's many other sources of interest. So what we talk about is really what some people consider hard X-rays. These are also the kind of X-rays that were used for the first demonstrations back in the end of the 19th century, which were really applied for radiography, but nowadays use X-ray for everything. Like when checking at the airport, they check your bags, non-destructive testing, cargo inspection, at the dentist for X-ray diffraction. It's basically everywhere. But still, we would like to improve upon X-rays in some ways, and compact, bright X-ray sources we can generate with laser plasma interaction are interesting in some ways, because on one side you can probe matter in an interesting way, because these sources are usually very short. So you can do time-resolved experiments, which is interesting for physics and chemistry. You can also use new imaging modalities, because these sources sometimes have spatial coherence or so you can do phase contrast imaging, or you can tune different energies. That's interesting for biology and medicine. And to some extent, you can also excite matter, like during ionization heating and so on. So let's now go back and motivate this a bit more from a theoretical standpoint. The emission of X-rays can basically be explained entirely with this formula. But it's a bit daunting of a formula when you see it, equation, when you see it the first time. So don't panic, we're now going to explain briefly where does this equation come from, motivate it a bit, and then look at it, what it tells us, how we can actually generate X-rays using electrons. And that will then tell us a bit about how we can design a laser plasma X-ray source or an X-ray source in general. So as always, when we talk about fields, we start with Maxwell. And so if you have any charges that interacts with the fields, and from the Maxwell equations, from the differential equations, usually what you do is say electrons, just like delta functions, and you can integrate it, get the potentials, and from potentials you get the fields. And this is the solution for the electric fields in space and time. And so this is also a rather big equation, and it has two important components. This is what's called the near field term. This is where we have all these things like the inverse square law when a charge is not moving, and this reduces just to inverse square law dampening. But the other component here, which is the one here interesting, is the far field, what's emitted further away. And there's three interesting components to this formula already. So n, this is a vector pointing to our observer. To make it easy, you can, like we will usually consider it to be like on axis, so this is basically like 1, 0, 0, something like that. And then beta is the velocity, and here we have a term which is acceleration, so the time derivative of the velocity. And we can get now from this equation to the one that I showed in the beginning in basically doing 3 steps. So the first step is that this equation is described in terms of time. So we have to do a Fourier transform to go to frequency. So that's basically this term over here. So this is the transform. Then we calculate essentially the pointing vector to get to something that's kind of energy. And then we have here the retarded time, and to go from retarded time to the real time, we also have to make a coordinate transform. So that's essentially briefly what's happening there. You can look it up in Jackson, but this is basically an idea where it comes from. So let's now look at the parts that make up this equation. And the first one I want to look at is the one here on the bottom. So you might remember that 1 over 1 minus beta square is actually the Lorentz factor square of an electron. And so if we look at this term over here, this one here, this is essentially gamma squared. And so this tells us that the radiated energy increases with gamma squared. So the higher energy the electrons are, much more energy is emitted. And so we need high energy electrons and hence some kind of accelerator to get them in the first place to radiate a lot of energy. Now, the second part, which is interesting, is this one here, the acceleration. If this guy here is 0, this whole term is 0. So you need acceleration to emit radiation. If a particle is not accelerating, you can basically boost into its frame of reference and it's stationary. So, but if it's accelerated, you can't do that, and then you have radiation emission. So you need acceleration, and particle will radiate. And so the easiest way you can generate X-ray is you start with something which is like high energy, and you just slow it down very quickly. And this you can just do by taking some electrons, you shoot it in something like tungsten or so, and you just slow down to 0 very quickly, and you get what we call Bremsstrahlung emission. But there's more to this formula because there's actually a cross product there. And this means if you want to look at forward emission, it's actually much more efficient if we accelerate the transverse direction, because then with the cross product you get more forward. And so what we actually want is something that is jiggling, wiggling our electrons in the transverse direction to the movement. So if they move this direction, we want to jiggle them in this direction, and it's much more efficient than doing it in this way. And then the last component I want to talk about is this guy over here. This one here, we better go through it calmly afterwards once again. It's essentially 1 minus beta. Like you can rewrite this R over C is basic velocity, and that's again with the relation between beta, the velocity, and the Lorentz factor. You can rewrite this in terms of gamma, the Lorentz factor of electrons, and then we find this upshift, which is often discussed in undulator sources, which is this gamma square upshift. If you jiggle around something at a frequency omega, then actually the emission will be at 2 gamma square. This is essentially a relativistic Doppler effect, but it also drops out typically from this formula. And so this is actually probably the most interesting part about synchrotron sources, because it means if you have an electron which has, say, a gamma factor of 1000, which is like 500 MeV, and you jiggle it at some frequency, the emitted frequency that an observer on axis will see is 1,000,000 times higher. And so you can move an electron at like on a period of millimeters, but the emission is at nanometers. And so this is a very efficient way to upshift the frequency. So to summarize now, what we learn from this formula is to generate bright X-rays, what we need is an accelerator to get high energy electrons. We need some kind of transverse acceleration of them to get more efficient radiation emission in forward direction, and the frequency is dramatically upshifted, so the higher energy we use, much higher energy is emitted, because we have this gamma square factor there. So how can we actually wiggle around electrons? And this is actually very simple conceptually, because the only way you can actually interact with electrons is the Lorentz force. So this is like charge on electron cases minus E, and this is what you have at your disposal to interact with your electrons. So either you choose the E field, and you just put it in some field that is like electrostatic, has a certain potential, and then the electron will just move up and down due to the electrostatic field. You could use something which is a combination of E and B, like a laser field, that's an electromagnetic version, or you can use only a changing magnetic field. And so this is actually then associated with different kinds of radiation sources. So this purely magnetic one, as I will show you on the next slide, is what we call magnetic undulators. That's the technique that's used in most synchrotrons and light sources around the world at this point. This one here is actually like the equivalent to Compton scattering. Now, Compton scattering is like the quantized picture of this, but it's exactly the same process. I won't talk about it today. It's like an entire idea that you can scatter electrons with a laser. And it's also done with laser plasma accelerators. So I won't focus on this guy here, which is photon radiation, which is a bit more advanced already. So the conventional way now to build a light source is that we start with some electron source. These electrons have a duration of nanoseconds or picoseconds. We accelerate them with a radio frequency cavity. Fields here, radius usually like tens of megawatt per meter. Then we have some beam optics. It's like some Tesla per meter. And overall, the entire size of this thing is like tens or hundreds of meters for like a linear activity. And then we have this part here, which is the undulator. And so the undulator is like a stack of magnets which have alternating fields. And typically we have a period here of some millimeters or centimeters over which these fields are inversed. And so this gives you this jiggling wavelengths, which is in the millimeter or centimeter range. And so synchrotrons usually use like GeV electrons, so a gamma of a vector of 2000, 4000 to dramatically upshift that to reach the X-ray region. Now what we go and do with laser plasma sources is totally change the scale on which these things are happening. And I'm not sure, like, did you discuss already laser plasma sources in the lecture? No. So in the laser plasma accelerator, the duration of the electron beam is much shorter because the entire structure is on the scale of micrometers typically. So we get a femtosecond duration. The accelerating fields are all of the magnitude higher. So we're talking about tens, hundreds of gigavolts up to terawatt per meter. And this is actually really important because it means that we can change the size of the whole thing from tens, hundreds of meters down to some millimeters or centimeters. And another thing that's really interesting is that in these accelerators, so this is this accelerating structure, which we probably have seen in the lecture, we have these really strong longitudinal fields. But at the same time, we have equally strong transverse fields. And so what we can do is we can actually use these fields to accelerate the electrons, and at the same time use these fields here to jiggle down the electrons all in one. And so this is a very convenient way because it means that you can, without any additional devices to generate the radiation, get everything in one step. So you don't need the accelerator and then what's called an insertion device to some undulator, wiggler to generate the radiation. You get everything in one. And so this looks a bit like this, that we have the laser here on the right. It goes into a plasma and it forms this structure behind it, the plasma wave. In the plasma wave we have strong accelerating fields in the back where we would accelerate electrons. And then these electrons, you see, they are moving a bit up and down. That's what we call beta-tron oscillations. They are motivated by these transverse fields that I was talking about. And because they are both energetic and they are moving in transverse direction, we get this beta-tron X-ray emission. And this radiation has some really interesting properties. So it's a broadband, multi-kV X-ray source, a hard X-ray source. But probably more importantly, because of the size of the whole structure, the plasma wave, being only a few micrometers, the source itself is also very small. It's a fraction of that because it originates from that bubble, right? So it's like from somewhere in the inside, and so the source size is just a few micrometers, which is much less than you would have in a Brandstrahlung source, conventional source. So this source has a high spatial coherence. At the same time, the duration is also, for the same argument, very short because it has to fit into these 10 micrometer volts. And so these laser-driven beta-tron sources have already been applied for various applications in imaging, mostly. And one of them is phase contrast imaging. So here you use this property that your source has a high spatial coherence. So everything originates from the point here, and then you have some sample, and then you get these fringes, and it passes the object. Is essentially the same as you have in optics when you illuminate something with a coherent light source. So you get these fringes there, but these fringes tell you something about the structure of your object, and they are very sensitive to changes in the basically refractive index of your material. And so you can see things that would usually be transparent, like say an insect. It's usually transparent in absorption contrast. Like if you send X-rays through them, they are basically not absorbed at all. But we can still see clearly the inner structure of all these insects here because we have this edge enhancement. At each edge, which is a slight change in the refractive index for our X-rays, we get these bumps, and then we can really see that. Also, we can use the same sources for tomography then. So in tomography, we take different views of the same object, and we can then reconstruct the 3D structure. But so far, this was really proof of concept because this measurement, for instance, took 5 hours to make. It was published in 2015. And similar measurements were also done in a bit more real-life objects like bone samples and mouse embryos, each time as well taking a few hours to do. And so I will show you later how we can now improve upon that. So this kind of concludes the first general introduction about these sources, and now I want to move to a few examples how we can learn more about these sources with what one might call machine learning. And so the first question is, how can we actually know the spectrum of an X-ray source in general? So maybe you've done some practicas here in physics where I don't know if you still do the K-alpha source here, aber I know that on that CPU. What you can do is you have a detector like this, which has like a small semiconductor piece, and each time it's hit by X-ray, it releases a defined amount of electrons. So each, in this case, each 4.4 eV of photon energy that's absorbed, an electron is released. So as an example then, if we take a 20 kV photon that's entirely stopped inside my detector with 100% efficiency, that means then I generate 4,500 electrons. I can count those and then tell, okay, that was the energy of the electron. And so you see that for this detector, we have this up to like 60 kV, we have 100% efficiency here. So you really know, if you count the electrons, what was the energy of these X-rays. And the detector then runs at a very high readout rate, so typically like 100 kilohertz. So it's a microsecond integration time, and then it builds up a spectrum from all these events that it's counting. You can also do the same thing then essentially in 2D. So you have a lot of these pixels around, and then you can look at the spectrum that you're generating in different ways. The problem is that this doesn't work with betatron radiation. And this is because the betatron radiation is so emitted over such a short time. So to talk about these femtoseconds. So if we look at our integration time, it's microseconds, and then we have this flash of betatron radiation. We cannot distinguish whether it was one high energy photon that released X electrons, or it's maybe 2 or half the energy, or some weird combination. We just don't know because we're integrating over microsecond, but everything comes in a few femtoseconds. And actually the case is much worse because it's so bright that usually you will get hundreds of X-ray photons that would hit your detector, and so you have no idea what is actually the energy. Now, one solution would be you can just reduce the X-ray flux. Like you can just go far away, inverse square law, so you get less and less photons. You reduce it until you just have one photon. And then you do again this single photon counting. But that's rather impractical because one way you would have to go really far away. We're talking usually like tens of meters here. And most labs you don't have that space. And the other thing is you still have to build up your spectrum. And even if you would use such an array detector, you would need a lot of events. And these sources that we're working at the moment with high power lasers typically operate at a hertz or less actually. Like there are efforts to bring it higher to 100 hertz, kilohertz, but at the moment it's just not practical. So what we want here is a single shot solution which can really handle a high instantaneous X-ray flux, but still tell us what is the spectrum here. And what we can use here are the actually the attenuation properties of matter when it interacts with radiation. So you probably know the Beer-Lambert law that if you have some intensity, initial intensity, and you go through some material, the transmitted intensity is determined by the mass attenuation coefficient. And so this is basically you integrate over this mass attenuation, over the distance that we have here. This is this integral here, this determines how much absorption is happening, and so then we have this exponential dampening by this factor. And this is an effect which is actually energy dependent. So most materials, they are more attenuating for like low energy in many X-ray cases, and then you have the higher and higher the energy, the more transmitted it is. So this is actually the idea behind absorption contrast, right? Like you have bones which attenuate more and other materials which attenuate less, and then you get contrast. And so this entire thing then depends on multiple things. So it depends, as I show here on the right, on the atomic number. So the heavier the element, the more it absorbs. Like you know, lead is usually used in radiation protection because it absorbs a lot, whereas aluminum is not really shielding a lot. So aluminum will be somewhere here, lead is here if you want. And so you see there's much more attenuation. And also because there's much more electrons, we have these edges here. So these are these absorption edges where you resonantly absorb. This is the K edge, this is the L edge, and so forth. And so the X-ray attenuation depends on atomic number, the energy, as I explained before, and the thickness, obviously. Like if I have a very thick sample, it absorbs much more. And you could also play with density, but in most, like in the attenuation coefficient, we have this per kilogram. So essentially, when you change the density, you do the same thing, but that's usually not really an option. And so what we can do is we can take a combination of different filters that have different attenuation, can be different materials, or more simple, as I show you on the right, can be the same material but different thickness, and all these will absorb differently. So in this case, for instance, there is a simulation where we take aluminum, like very thin sheets, 3 micrometers, which basically transmits everything. It just cuts away by maybe like 3 kV or so. But then if you use 3 centimeters of aluminum, up to 100 kV, basically nothing passes. So this is then distributed logarithmically. And so now what we can do is we can say we have some kind of spectrum that we don't know. This is our ground truth. This is actually a Betatron-like spectrum. And then each of our filters will show a different transmission, right? So if we have the 3 centimeter filter, it basically transmits nothing, as I said before. The very thin one transmits everything, and then we have the scale in between. And now what we can do is, since we know all these laws, we can say, oh, I start with some guess, like I know probably I generate X-rays, so let's start at 50 kV. And I know the spectrum, I know the filters that I have, and I know the attenuation properties, because that's measured and tabulated. And so I can calculate an expectation for that guess. And that looks like this. So in this case, we have this distribution, and we see that if this were the actual spectrum, it would transmit far more in this range here. It would be much more transparent, because we don't have any low energy X-rays, so the thin filters, they don't absorb at all. So we already know, oh, this is too transparent, the energy is probably too high. So I can adjust that and put down the energy a bit, but I see, oh, this is still too transparent. And then I can go further down and see, okay, now it's getting better, but now we see far too much attenuation, because we don't have any component here, the 60 kV or so. And so all these filters are now dark. And so then I can say, oh, probably I need a bit more high energy, and I can increase that. And now it's actually looking very similar. And maybe you would say, oh, actually these two are the same, but let's look maybe better at the difference directly. And so now if we look at the difference, we see, oh, these are very similar, but there's still some difference, and I'm now going to change the color scale so that we can see it better. And so there is still a significant difference between these middle filters here. And so what I did now was I took the absolute difference between each of these filters transmissions. So the one that I measure in the experiment and the one that I guess I would have for the spectrum. And then what people conventionally do is that maybe they look at the squared difference. So this emphasizes more the ones where you're wrong. And so then we see, oh, we are mostly wrong in this range here. And this is then the squared attenuation difference. And this is still like a bit complicated, because it's like a lot of numbers and you have a lot of filters, you have a lot of places to look at. And so what people then like to do is usually they sum it up to reduce it to one single number. And this is what we call the mean squared error. And we can use this as what's called a loss function that determines how good is actually this guess that we had. And if we further improve our guess now, we knew like we want a bit more in this range here, so we change a bit the properties, we see, oh, this number is further going down. So what we just did is we reformulated the problem of retrieving the spectrum to the problem of finding the minimum of this loss function here, of this sum over the squared filter differences. And this is actually a very common problem that we might also already have encountered in different circumstances, which we can solve in many, many different ways. And one common way is to use gradient descent. So in gradient descent, you basically walk along the slope. So you take a few measurements, see like in which direction is it getting better, or like you see the direction where it gets worse, and then you walk the opposite way. And so you walk like down that gradient. And it's a really nice technique. but it really likes to get stuck in minima. So it walks down, but if there's like a local minimum, it doesn't really get out of it. And so what you usually have to do is you initialize it many times with random starting points, and then eventually you find more or less where the global optimum sits. But there's also more advanced algorithms. So for example, the expectation maximization algorithm. Here we incorporate some knowledge about the statistical distribution of our measurements. And then we do a very similar thing to this one. We maximize, and this is like one thing already, like in machine learning, like people always switch between minimization and maximization. It depends on the community. So this algorithm comes from a community that likes to talk about concave optimization and not convex optimization. So here we maximize now this function, and it's a bit different in the properties. Really would be too much now. But if we use it, as you can see, we get a better estimate already. So before we were with this by hand thing, and now with this one, we already get a much better estimate. And then there's even more, even other methods that you can use. So one is you can formulate the problem as an inversion problem. So you say, I have these measurements, I know how to get there. How can I invert that? So you know, like we know how to simulate the thing, and that is some kind of matrix multiplication, so we can always inverse that matrix that we use to get there. Again, this is now extremely short. And then you can calculate the inverse. Most problems will be pseudo-inverse because the matrix is not squared. And this, in some cases, works really well. So this is actually the result from using the pseudo-inverse, where you can see we get an extremely low error. And what is great about this technique is it's one shot. It's like it doesn't need to iterate like a gradient descent or so, where you need to evaluate your function thousands of times, but this is just done a single time. So you calculate once your inversion matrix, and once you get a new measurement, you can immediately tell, oh, this is what I guess the spectrum is. Now this is a case in which the pseudo-inverse works really well, but in practice sometimes it's not as stable because it can still have like negative solutions and so on. So what you can also do is, which is basically an extension of this idea, is to use neural networks. So neural networks is also essentially matrix multiplication. So you have used the neural network to approximate what your inversion for your problem is. The problem there is you made some training data. So you say, oh, these are all examples that I calculated, and from there, please generalize, tell me what is the best fit between all these examples that I've shown you. And this is like that's a really tricky part. What are like plausible spectra? So the thing is, for all these problems, there's usually some random noise solution. So there's some solution which goes like really crazy around it, which is also a near perfect solution. So you can essentially say, oh, I only want like smooth spectra or something. So you have to put something in that you say, oh, I think it's more like that. And so this is some kind of prior knowledge that you can incorporate to improve the output of this. But yeah, so this can also work very well, but you have to be a bit careful how to design like what examples you give it. So for instance, if you would just train it with these Gaussians that are used here, so these were all just normal distributions. If you would just train it with that, it's the only thing it has ever seen. It will never be able to go more abstract. But what you can use is you can use sometimes called Gaussian mixture. So you can use a lot of Gaussians in which you can combine to essentially form any type of slopes that you want. So this very basic problem, like we have a lot of filter measurements there, and it somehow constrains where our solution sits, but it's like underdetermined because obviously you have less measurements than the point you're trying to reconstruct. It's a very typical problem in experiments. Like usually you have less measurements than what you're trying to find. And so I really like this problem because it's it illustrates a bit, gives an idea of techniques that can be used. This is an example where we actually used an experiment. So this was done using this EM algorithm, the iterative one. That was the one we actually was before we were using the inversion formulations. And it works rather well. It even recovered this dip here. So this comes from the fact that we're actually measuring our X-rays outside of the chamber, and there's kind of a window, like an aluminum window. And this aluminum window will cut part of the spectrum. So the recovered spectrum had this dip that we actually expected it to have, that there's like nothing below 5 kV, which is cut away. In a very similar problem to this is actually the tomography that we talked about before. So in the tomography, we have something like some bone, and then we look at it at different angles. So this is one angle, another. And then what we can do is we can look at single slices of our problem here. So these are all of the illuminations at different angles. And then we can stack these together, and that's what is called a sinogram. So you stack from like 0 degree to 180 degree to take all these slices, you stack them together, and you can see that the structures are essentially like moving around as you're turning and you're looking through the sample at different angles. And now the problem that we need to solve is how we can do the back projection. How can we use these measurements that we have taken and go back to the initial bone structure that caused that measurement? And so the oldest and standard way to do that is using what's called the radon transform. So we start with a sinogram. Now, first step is a Fourier transform. I think I skip over the motivation here. Essentially, this part here, this is organized now in angles. So these are different angles at which I look through my sample. And then in the Fourier space, I can then rearrange all these different measurements in a circle. So this is like our zero frequency, and then we have all the different observations and circle stacks these together. The thing is, when you do this kind of thing, you have very high resolution here in the center because all the slices are overlapping, but you have low resolution outside. At the same time, this is not really good to have high resolution there because you always have noise, and so actually like blurring out a bit because they are all overlapping in this region. And so what you have to do is you have to kind of design a filter that emphasizes these different aspects, that you have like bad resolution outside, but maybe the center is a bit blurred. And so people design some kind of filter. This is where the filtered back projection comes from. And then you just go to the image that you wanted to reconstruct. Now this is basically, I see it a bit as the equivalent to this, this inversion approach that we discussed earlier, like inversion metrics. I see it's a bit similar because it's like some operation, like some function, the radon transform you apply to your function, and then you use the inverse radon transform to find what you did. The thing is, with this approach, very similar to the inversion metrics one, it doesn't really like anything that is irregular or noise and stuff like that. Like if you have the perfect problem, it works really well because it's an analytical solution to it. But if you have something like slightly irregular angles or you have image noise, it really gives what's called artifacts in the reconstruction. And problem is with the better tone X-ray, we actually have these kind of fluctuations rather frequently. So you get a lot of good measurements, but sometimes there's an angle for which the source was a bit dark. And so this results in big problems then. So this is an example for that. Because what we did here was, in contrast to the measurements which I discussed earlier of these tomographies that took hours, we were like, we don't want to take like 10 shots at each position because that means the measurement is 10 times slower. But we want to take just a single shot per position and rotate also at every shot we rotate the angle. So this meant that there were a few shots that were actually quite dark. And if you apply filter back projection, then unfortunately you can't see it well on the beamer here. There's here's strong wind artifact, so this is, you can see a hint of it. Like on a better contrast, you will see there's a lot of noise actually in this image, and this comes from these reconstruction problems. And so what we can do is we can use machine learning, actually something that's basically this spatial version of this expectation maximization algorithm to suppress that noise, because it's a statistical method, it iterates, and it's much more robust to this noise. Also because we can use regularization, so some smoothing inside the iterations. So because this is like one shot, you cannot really do anything. Here you can try to regularize and suppress these things. And in these images, we don't have any artifact. And so this was then really nice, because we could show that we could use just one shot per position, rotate 1 degree each shot. And when we combine that with operation at 1 Hertz, we could do the entire measurement now in 3 minutes compared to 2-3 hours before. And now there are even lasers that work higher. So actually our laser at the time could work at 5 Hertz, but our X-ray camera couldn't. So we could have even done the same measurement in 40 seconds. And so, yeah, with like 10 Hertz systems, this is becoming really the kind of duration that is relevant for real life and less proof of concept. Now, last thing that I want to briefly mention, because it would be a topic of its own, you can also use machine learning to optimize the source itself. And essentially, you could use what we discussed before. You could use some gradient descent method or so to find the optimal solution. But as I mentioned, like gradient descent needs a lot of steps. You need like single steps to get first the gradient, and then you have to walk and walk and walk. So you typically need like thousands of shots. And gradient descent really doesn't like any noise. Like if you would have like fluctuations, it can just estimate the gradient to be actually the wrong way around. Like if you have some noise and you have like 2 noisy measurements, and depending how you take them, maybe suddenly you find that the gradient is this, and the real mean gradient goes this. So it's not really an option, and we need something that can incorporate knowledge of noise and also works with few shots. And so what's a technique that is really useful, and a few groups are adopting right now, is what's called Bayesian optimization. And essentially what it does is we take a few measurements and then we create a model how we think the landscape of our measurements looks. This is called a surrogate model. And so this is actually something that is also done in expectation maximization, but there you would just use a very simple function. In this case, we use something that's more general. It's called a Gaussian process. And so you take a few measurements, and then it predicts you how it thinks the landscape looks. And then it can tell you, based on what it thinks the mean values at the position, but also the uncertainty, where you should probe next. Because basically the model tells you, I know this is a good position, so maybe you want to probe there, but I also know I've never been in this region. I have a really large uncertainty. And so then it weighs these factors and can tell you, oh, maybe go in this region to want to see if there's anything there. If it sees there's nothing there, then it goes back to the good point. And so this is one example where this was applied to X-ray signal optimization by a group at Imperial College. And so what they were optimizing were 6 different parameters. So beta 2, 3, 4 is the dispersion of the laser, so the second, third, fourth order dispersion. They changed the focus position, how they focus onto their target. They change the density of the target, and then they could change the length of the target. And what you can see here is that the algorithm is actually changing these parameters a lot. So each of these colors represents like each of these boxes is one shot, and the color is like the value normalized, like of the range that it has to scan. And you see it's really jumping around a lot, then it finds like something where it's exploring similar values, and this is where it has this first quasi-optimum, but then it jumps around a bit again, like here it changes parameters and found a place which is even better. Then it explored around that region, found even better places. This is then when it found the optimum. And it's really, and at that point it was very certain that this is locally the optimum. And then what the algorithm did is it actually decreased again, because what it does, it goes in other region where still the uncertainty is a bit higher to see maybe there might be something of interest. But once you found the global optimum, you can basically abort them. So this is what it does here, is just make sure that this optimum that it has found is the actual one. And so this is a technique which can be extended in many ways. It's something we've been working on a lot recently. And so this last slide is just a bit of a summary of stuff that we've been doing, which is even more into the machine learning part. And so one is that we took this Bayesian optimization and we looked at it to not only optimize a single objective, say the signal, the X-ray signal, but we could at the same time optimize a second thing, like the divergence or some other property. And this is a very interesting problem, because in conventional optimization, you have to marry these two factors into one number. Like we saw in the example before, we were taking all the different filter differences, we summed them up, and then you have this one scalar number that you're optimizing. So this process, they sometimes call it scalarization, because take a vector, make it in a single number, and you have just a single number you want to improve. But what happens if you have two different things, sometimes even competing things? So say you have electrons, and you want to improve the energy and the charge. Now we have energy conservation, right? So these two are linked together. You cannot, like if you increase the energy a lot, you will suffer of the charge that you can accelerate, because you only have so much energy available, and the other way around. So we have this kind of trade-off here. And each of these trade-offs has actually a trade-off curve. It's called a Pareto front. And so what we did is like we incorporate algorithms that can look at all these different objectives, and then even more, it can work with different models that have different fidelity. So for instance, if you run simulations, simulations sometimes run at different resolutions, like you want to run a quick simulation to see a bit how is your space, but then if you really want to produce results for a paper, you need really high resolution. Now this algorithm marries the two together, like it can take the information from the low resolution ones, then takes a few points at high resolution, it actually chooses which resolution it needs, and then it can get a good prediction how your system would behave at high resolution. And this, what's really cool is that we discussed with some people at Facebook who are developing this code, PyTorch, and they actually now implemented our algorithm in their code, which will be released in a few weeks as the 1.0 version of this Bayesian optimization torch. And we did also a few other things. It's a very active topic, so something I'll show here a bit, which was surprisingly straightforward, was using object detection algorithms that you can use in an experiment if you want to find, for instance, a damage that's happening in your laser system, or you have some structure that is disappearing, but that's a bit hard to describe. Like in this case, we have a plasma wave here. It's like hard to actually see by eye, and it's even harder to write a code that would identify the region, but these object detection networks work really well with that. And then we also applied these things to beam diagnostics, like all these inversion problems. They are very general. So for instance, wavefront sensors, they have the same problem. So we use these techniques there and work on hyperspectral sensors with compressed sensing and these things. So as a last advertisement, if these things sound interesting for any of you, we actually have an opening for what's called CALA postdoc position, which is like a 1-year funding, which is open at the moment. And I also have direct funding for PhD or postdoc positions in my group. So if anybody is interested, just contact me. I'm also around until tomorrow. So.